Scene script. Have you ever wondered how water travels from the roots of a plant to its highest leaves? This marvel of nature is due to a phenomenon known as capillary action. Capillary action is a process that allows liquids to flow in narrow spaces, even against the force of gravity. It's an essential mechanism behind many natural and man-made processes. For instance, it's the force that guides water through the tiny veins in a leaf or ink through the fine tip of your favorite fountain pen. One of the most compelling demonstrations of capillary action is the rise of liquid in a capillary tube. A tube so small that it allows liquids to flow upwards, seemingly defying gravity. It's as if the liquid has a mind of its own, creeping up the walls of the tube without any external assistance. In our exploration today, we'll dive into the science behind the rise of liquid in a capillary tube. Scene script. Before we delve into the details, it's important to understand some basic concepts. Firstly, let's talk about surface tension. Picture this. You've probably seen insects walking on water, right? How do they do it without sinking? The answer lies in surface tension. Surface tension is the property that allows the surface of a liquid to resist an external force due to the cohesive nature of its molecules. It's like an invisible skin on the liquid surface, which is why that bug doesn't sink. Next up is density. Simply put, density is the mass of an object divided by its volume. Think of it as how much stuff is packed into a certain space. For example, a kilogram of iron has less volume than a kilogram of feathers, making iron denser than feathers. In the context of capillary action, the density of the liquid will influence how high it can rise in the tube. Now, let's move on to the contact angle. The term might sound a bit intimidating, but it's really just the angle at which the liquid meets the surface of the solid. If this angle is less than 90 degrees, the liquid will rise in the capillary tube. If it's more than 90 degrees, the liquid will be depressed. This is all due to the intermolecular interactions between the liquid and the solid. These three concepts, surface tension, density, and contact angle, are the key players in the phenomenon of capillary action. They dictate how and why a liquid moves the way it does when it comes into contact with a small tube or capillary. With these concepts in mind, we're now ready to delve into the process of liquid rising in a capillary tube. So, what happens when we dip one end of a capillary tube into a liquid? Let's imagine this scenario. We have a tube of small radius, a capillary tube, and we immerse one end into a liquid. What we'll observe is that the liquid either rises or falls within the tube. But why does this happen? It's all about the interplay of various forces and characteristics of the liquid and the tube. The first thing we need to know is the contact angle. This is the angle formed between the liquid surface and the surface of the tube. If this angle is less than 90 degrees, the liquid rises. If it's more than 90 degrees, the liquid falls within the tube. Now, let's consider a tube of radius r dipped into a liquid with surface tension S and density Rho. The surface of the liquid inside the tube is nearly spherical due to the small radius of the tube. Let's analyze the forces acting on the portion of liquid that has risen in the tube. Firstly, there's the force exerted by the surface of the tube on the liquid surface. Secondly, there's the force due to the air pressure above the liquid surface. Thirdly, the force due to the liquid pressure below the surface. And lastly, the weight of the liquid itself. The liquid surface inside the capillary tube meets the tube wall along a circle of radius r. The force exerted on the liquid surface by the tube surface across this contact circle can be calculated using the formula 2πrs cost, where theta is the contact angle. Next, we have the force due to the air pressure outside the liquid surface, which is ppr squared, where p is the atmospheric pressure. This force acts vertically downwards. The pressure at the bottom of the risen liquid is equal to the atmospheric pressure, since it is in the same horizontal plane as the free surface outside the tube. This force acts in a vertically upward direction, So we see that the forces due to the air and liquid pressures cancel each other out. The balance is maintained between the force exerted by the tube surface and the weight of the liquid. If the height raised in the tube is h, and we neglect the weight of the liquid contained in the meniscus, the volume of the liquid raised is pr squared h. The weight of this part is then pi r squared h arg. Thus, equating this weight with the force exerted by the tube surface, we get h equals sine 2s cos arg. This equation tells us that the height raised is inversely proportional to the radius of the capillary. If the contact angle is greater than 90 degrees, the liquid is depressed in the tube. To account for the weight of the liquid in the meniscus, we can make a correction if the contact angle is 0. This is the case with water rising in a glass capillary, where the meniscus is hemispherical, and that, in a nutshell, is the process of liquid rising in a capillary tube. Now that we've understood the process, let's delve into the math behind it. The height that a liquid rises or falls in a capillary tube is given by the formula h equals 2s cosine theta divided by rrog. But what do these symbols represent? H is the height of the liquid, s is the surface tension of the liquid, theta is the contact angle that the liquid makes with the tube, r is the radius of the tube, rho is the density of the liquid, and g is the acceleration due to gravity. So, how do we arrive at this formula? Well, we start by considering the various forces acting on the liquid in the tube. There's the force exerted by the surface of the tube on the liquid, the force due to the pressure of the air above the liquid, the force due to the pressure of the liquid below, and the weight of the liquid itself. The force exerted by the surface of the tube on the liquid can be calculated as 2 pi rs cosine theta. The forces due to the pressure of the air and the liquid cancel each other out, leaving us with the weight of the liquid, which balances with the force exerted by the tube. The weight of the liquid is given by pi r squared h rog. Equating these two forces, we get the formula h equals 2s cosine theta divided by r rog. This equation tells us that the height of the liquid is inversely proportional to the radius of the capillary, and it depends on the surface tension of the liquid, the contact angle, and the density of the liquid. Interestingly, if the contact angle is greater than 90 degrees, the term cosine theta becomes negative, and so the height hh also becomes negative. This explains why the liquid gets depressed in the tube when the contact angle is greater than 90 degrees. This mathematical equation beautifully captures the physics behind the rise of liquid in a capillary tube. But why does all of this matter, you might ask? Well, the fascinating phenomenon of capillary action is not just confined to our science labs. It has significant real-world implications that are integral to our everyday life. For instance, it's the driving force behind the survival of plant life on Earth. The roots of plants absorb water from the ground, but how does this water reach the topmost leaves of a tall tree? It's all thanks to capillary action. The narrow xylem tubes in the plant stem act as capillary tubes, allowing water to rise against gravity and reach all parts of the plant. Moreover, capillary action plays a crucial role in the functioning of inkjet printers. The ink in these printers is stored in narrow tubes. When a print command is given, the ink gets propelled onto the paper. The movement of ink from the storage tube to the paper is facilitated by capillary action. So, every time you print an assignment or a picture, capillary action is at work, and it doesn't stop there. Capillary action is also essential in medical procedures like blood tests. When a small sample of blood is drawn, it moves up the narrow capillary tube due to the same principle. These examples illustrate that understanding scientific phenomena like capillary action is vital. It helps us appreciate the intricacies of the natural world and the technological marvels we often take for granted. It also opens up possibilities for innovation. By understanding capillary action, we can design more efficient irrigation systems, develop advanced medical equipment, or even create innovative artworks. So, the next time you marvel at the height of a towering tree or use a pen to jot down your thoughts, remember the subtle yet powerful phenomenon of capillary action at work. You see, science isn't just about equations and lab experiments. It's the magic that makes our world fascinating, functional, and full of wonders. So next time you see a tall tree or use a pen, remember the subtle yet powerful phenomenon of capillary action at work.